Hello there. In this lesson, we're going to learn about light refraction. So refraction is different from reflection. And you can kind of see both here. You can see a little reflection of the girls' faces right in front of them on the water. But also, there's some weird stuff going on here when you look at their hands, which are under the water. And that warpiness that you get when light goes from one substance to another substance, well, that's refraction. So the fancy word for a substance that light can pass through is a medium. And so air would be a medium, and water is a medium, and vegetable oil is a medium. Glass would be a medium. And so when the light goes from one medium into another medium, it changes speed and it can change direction. So you can see that when the air and the glass is the only mediums that the light was passing through, that the straw is in this location, and then something happened when the light went from the water into the air, and you can see that there's like a change in direction of the straw that's in this glass of water. Same thing for the legs underneath the water here. They clearly don't look like they would if they were above the water. If you recall from our first lesson in optics, we discussed how light is this electromagnetism that has a whole range of frequencies and wavelengths. And as it goes from one medium, like air, into another medium, like glass, those different frequencies and wavelengths get separated. The speed of the different forms of light slow down, and you end up with this whole spectrum on the other side, including a whole bunch of frequencies that our eyes can't even detect. So you've seen this in real life, I'm sure, if you've ever seen a rainbow. The droplets of water that are still in the atmosphere are doing the same thing. They're breaking up the light into its whole component parts. And you also kind of see this every time you watch a nice sunset or a sunrise. And that is because the violet and the blue and the green light bends more. Most of that light goes straight into the earth on the other side that we can't see, and what you're left with is the reds and the yellows and oranges that are the ones that bend the least, and so are the last colors that you see in the evening and the first colors you see in the morning. So oftentimes when you have transparent substances, you will end up with both reflection and refraction happening at the same time. If you look at these sunglasses, you can kind of see images being reflected off the surface, but you can also kind of see my eyes underneath there and some of my cheeks, that sort of thing. Same over here in this pond, you could see the images of the trees up the ridge being reflected off the surface, and also some of the leaves that are lying in the bottom underneath. Alrighty, so similar to when we were looking at reflection, we need ways of measuring what happens to the light rays when it goes from one medium into another. So we're going to start off by adding an incident ray, so that's going to be a light ray coming from a source somewhere. And we'll put in our normal line, just like we did with the mirrors. A normal line will be 90 degrees to the surface where one medium meets another. And then, of course, you're going to have a refracted ray rather than a reflected ray. And you can measure the angle of incidence from the normal over to that incident ray, and the angle of refraction from the normal over to the refracted ray. This symbol here is a theta that's often used to represent angles. So one way of comparing the speed of light in different substances is by using the index of refraction. So the index of refraction is worked out by determining the ratio between the speed of light in a vacuum to the speed of light in some other substance. So we're going to use a formula to do this. The symbol for the index of refraction is this n. The symbol C is for the speed of light in a vacuum. It's the same C from E equals mc squared, Einstein's famous equation. And then the speed of light in the other medium is this script D V. So the speed of light and other medium. So if we're going to work it out for glass, we'll say N equals, the C is 300,000 kilometers per second, which is really, really fast, out in space where there's nothing to impede it. And then for glass, it's 197,000, so 197,000 kilometers per second. And if you type that into your calculator, you should end up with 1.52. So the index of refraction, because the units are the same on the top and the bottom, they cancel out. So it's a unitless measure. All those units cancel out. So the other way that you can get the index of refraction is by measuring the angles of incidence and refraction as well. So if you put on our incident ray, put on our normal, and put on our refracted ray, we can measure those angles and determine the index of refraction that way too. So put on our protractor and we see that we have a nice 50 degrees for our angle of incidence. So it's going to be sine of 50 degrees. And the angle of refraction is going to be the sine of 30 degrees. So if we type that into our calculator, the sine of 50 is 0.766, and the sine of 30 is 0.500, which means the index of refraction in this substance is 1.53. Same as the other one, so it must be glass. You can also use a little bit of math to rearrange this equation to find other angles. As long as you have two of the unknowns, you can always figure out the third one. So in this question, we're given a 25-degree incident ray angle, which would be this guy, and it's in glass, which means we're going to use our index of refraction of glass, which is this guy, and so we're looking for this one to solve things. So rearranging, you'd end up with sine of the angle of refraction is going to equal the sine of the angle of incidence divided by the index of refraction. So that means sine of 25 degrees all over the 1.53. Sine of 25, using my calculator, I get 0.4226. Divide that by 1.53, and that gives me 0.276. So that's the sine of the angle of refraction. So what you need to do is take the inverse sine or arc sine of this value here and up here. So sine -1 of 0.276 is going to be the angle of refraction, and it comes out to 16 degrees. So the last thing we're going to discuss here is a neat effect when you have light coming through from a substance where it's going slower to a substance that's going faster. And so since in those situations the amount of light bending is greater, it bends toward the normal, you end up with a point, if the angle is steep enough, that the light completely bounces off the surface between the two medium. You might have noticed this if you've ever gone to the bottom of a pool and sat there and looked up. You'll see right above your head, you can see out into the sky or the roof of the pool, whatever. But if you look to the side, you'll see a reflection of the bottom of the pool. And that's because the light is coming at you at a steep enough angle that it bounces off the surface of the water and back to your eye. Inside of binoculars, the same principle is used. They don't have mirrors in there. They have prisms. And so when the light comes in from the object that you're looking at, it goes into the glass, and then from the glass to the air again, the angle is sharp enough that you get this total internal reflection, and you use two of them to bounce that light around and through the lenses and then back to your eye. So finally, we can calculate that minimum angle that's required to get that total internal reflection by using another handy-dandy formula because, of course, this is physics. So the criteria, of course, is that the medium that you're coming out of has to have a greater index of refraction than the medium that you're going into, right? So first criteria satisfied, check. Great. Secondly, we can solve for this critical angle, this minimum angle here that's needed to get the complete reflection of all the light. And all we need to do is put in the values here. So sine of the critical angle equals the ratio of medium 2 over medium 1. So medium 2 is this guy. So that's 1.0003 for the index of refraction of air. And then we've got 1.30 for the index of refraction of the water. And if you calculate that or type it in your calculator, you'll end up with 0.7695. And then if you just want the angle, because that's the sine of the angle, we take the arc sine, which is sine -1 on your calculator of that 0.7695. And if you type that into your calculator, you get 50.3 degrees. So this angle here to get the total internal reflection is 50.3 degrees. All right. Well, happy calculating. We'll talk to you soon. I hope that helped. Take care.